Okay, so it says use the intermediate value theorem to determine if the function has a 0 on the given interval. So the intermediate value theorem states that we need to check the endpoints and see if what the signs are at those endpoints. So if I plug in I'm going to plug in these two endpoints into my function. So I'm going to do f of 0. If I plug 0 in there, I get 0 minus 0 plus 0 minus 2. And if I plug in 1, I'm going to get 2 minus 3 plus 4 minus 2. So 4 plus 2 is 6. 6 minus 5 is 1. And so what I see here is I see that the sign has changed. So I have a negative number and then I have a positive number. So that means that we must have a 0 on the interval. And if you think about this graphically, it makes sense because at 0 we're at -2 and at 1 we're at 1. So that means that it must cross somewhere in that interval between 0 and 1. And so this, the answer to A is yes, it has a 0. Okay, I can look at g of x, I could look at g of 0, which is this part of the interval, and then I can look at g of 2, and I can see if there is a sign change. When I plug in 0, I get 15, and when I plug in 2, I get, let's plug that into the calculator, we get 2 to the 4th plus 6 times 2 cubed minus 26 times 2 plus 15, and that gives me 27. So there is no sign change, and so the answer is that we don't know if there's a 0 or not, so can't determine. From the intermediate value theorem. Now we could look at a graph and determine it, but it's asking us to use the intermediate value theorem. So the intermediate value theorem is inconclusive if we have the same signs. Okay, so let's look at the very last one. We'll look at h at the endpoints. If I do h of 1 and h of 2, I can look at those. So I have 2 times 1 cubed minus 7 times 1 minus 14 times 1 plus 30. That gives me 11 for h of 1. And if I plug in 2, I get 2 times 2 cubed minus 7 times 2 squared minus 14 times 2 plus 30. That gives me -10. So I can see I have a positive one and a negative one on the endpoints of that interval. So this means there is a 0 for h of x on the interval between 1 and 2. Next, sketch a rough graph of that function. To aid in sketching the function, find the end behavior, zeros and multiplicities, and the y-intercept. So let's see what we can start with. The y-intercept is probably the easiest thing. So if I do f of 0, that's going to be 0 cubed minus 3 times 0. So that's 0. So f of 0 is 0. There's my y-intercept. Okay. Next, I want to find the zeros and their multiplicities. So I can factor that guy. So I get f of x is equal to, if I pull an x out of both of those, I'll get x squared minus 3. So that's a difference of squares that factors into x minus root 3 and x plus root 3. So those are my zeros. So at positive and minus root 3, I'm going to be going through like that. And next I want to look at end behavior. And so I see that this is a cubic, so I know they're going to be pointing in opposite directions. It is a positive, it has a positive leading coefficient, so it's going to be going up from here and down from here. So it should be doing like that, crossing through at each of those zeros because they have multiplicity of an odd multiplicity. Next one, sketch a rough graph of the function, end behavior, zeros and multiplicities, and the y-intercept. So if I plug in 0 for that, I get 2 times -1 squared times 1 cubed. So that just gives me 2. So f of 0 is 2. I can plot that there. And then my zeros are 1 and -1. So at the 0 of -1 is associated with this factor, which has multiplicity 3. So at -1, it's going to cross. And at 1, it has multiplicity 2. So the 1 is the one associated with this factor here. It has an even multiplicity. So at 1, it's going to touch and bounce. And then I want to look at end behavior. So it is a 1, 2, 3, 4, 5 degree polynomial. If I add all those powers of my multiplicities, I get a 5 degree polynomial. So it's odd degree, and it odd degree, and it has a positive leading coefficient, so it's going to go up on this side and down on this side. I know that at 1, since it has an even multiplicity, it's going to touch and bounce, and then it's going to go through there and then cross at -1. So it's going to look something roughly like that. The next one, use long division to divide the following polynomials. Give the answer as a quotient plus remainder divided by the divisor. Show all work. So I'm going to scoot over here a little bit because I need a little bit of space for long division. Okay, so I'm going to put underneath the 6x cubed minus 5x squared minus 3x plus 4. And I'm going to divide that by 3x plus 2. Okay, so first, what do I need to multiply 3x by to get 6x cubed? I'm going to multiply it by 2x squared. So now I multiply 2x squared by 3x, I get 6x cubed. 2x squared times 2, so I'm going to get plus 4x squared. And then I subtract that guy. That's going to give me a 0 there. And then minus 5x squared minus 4x squared is negative 9x squared. Minus 3x. So I'm going to multiply 3x by negative 3x, and that's going to give me the minus 9x squared. Negative 3x times 2 is minus 6x, and then I'm going to subtract that guy and see what I get from there. And so that gives me a 0, and then 3x plus 6x gives me 3x plus 4. So then I'll have plus 1, and I can multiply that by 1. And so I'm going to get 3x plus 2, and then I'm going to subtract that guy. And so I'm going to get 3x minus 3x, and then 4 minus 2 gives me a remainder of 2. And so I'm going to write this as a quotient divided. So I'm going to write this as equaling a quotient, which the quotient is 2x squared minus 3x plus 1 plus the remainder is 2 divided by my divisor 3x plus 2. Okay, so that's that one. All right, let's look at the next one. So we're going to do long division again. So I have 3x to the 4th plus 2x cubed plus 4x squared plus x minus 5, and I want to divide by x squared plus 0x plus 2, and I'm just putting that 0x in as a placeholder just so it keeps everything in line. And so I'm going to multiply the x squared by 3x squared to get that. So x squared times 3x squared means 3x to the 4th, and then I'll have 0x cubed, and then 3x squared times 2 gives me 6x squared, and I'm going to subtract that off. All of that. So that gives me 2x cubed, and then 4x squared minus 6x squared is minus 2x squared, and then plus x. And so next I'm going to multiply this by 2x. So 2x times x squared is 2x cubed. 2x times 0x is 0x squared. 2x times 2 is 4x. I'm going to subtract all of that, and I get negative 2x squared. X minus 4x is minus 3x minus 5. And so I'm going to multiply this by negative 2. Negative 2 times x squared is negative 2x squared. Negative 2 times 0x is plus 0x. And then negative 2 times 2 is minus 4. And so if I subtract that off, I'm going to get 0 there, and I get negative 3x. And then 5 minus negative 4 is 5 plus 4, which is negative 1. And so this is equal to 3x squared plus 2x minus 2 plus the remainder, negative 3x minus 1, over the divisor x squared plus 2. Okay, so next I want to use synthetic division to divide the polynomials. So when we're dividing by some linear factor, we can use synthetic division. And so I can set this up. My 0 is 3, and I have the coefficients are, the coefficient of x to the fourth is 1, 3, minus 1, 7, and 2. And you just have to be careful that your powers 4, 3, 2, 1, 0 are in order and there's nothing missing. If there is something missing, then you need to put a 0 in that spot. Okay, so I'm going to drop down the 1. 3 times 1 is 3. 3 plus 3 is 6. Times 6 is 18. 18 minus 1 is 17. 17 times 3 is 51. Oh my goodness, it's getting worse. 51 plus 7 is 58. 58 times 3 is 174. And then plus 2 is 176. So that's my remainder. And so this is giving me a cubic. So, and the coefficients are given there. And so I have 1x cubed plus 6x squared plus 17x plus 58. And then plus my remainder 176 over my divisor x minus 3. So that's another way to do that division. I can do synthetic division on the next one. So let's do it. And I have, again, we're going to have some zeros on this one. So the 0 here is minus 2. And so we have coefficient of x to the fifth is 2, x to the fourth, 0, x to the third, 0, x squared has a coefficient of 1, x has a coefficient of negative 5, and then the constant term is 1. Okay, so we're going to do that. So 2 times negative 2 is negative 4. So I get negative 4. Negative 4 times 2 is positive 8. So I drop down that 8. 8 times negative 2 is negative 16. Plus 1 is negative 15. Negative 15 times negative 2 is positive 30. And 30 minus 5 is 25. 25 times negative 2 is negative 50. And so I get positive, or negative 49 as my remainder. So this is equal to 2x to the fourth minus 4x cubed plus 8x squared minus 15x plus 25, using these coefficients here, equals my remainder plus my remainder negative 49 over my divisor x plus 2. Next it says use the remainder theorem to evaluate the polynomial at f equals f of negative 2. So the remainder theorem says that whatever the remainder is left over is going to be the value of f of negative 2. So we can plug negative 2 in here. We're going to do synthetic division. So 3, coefficient of x cubed is 0, then 2 minus 4, 1. Okay, so I can pull that 3 down. 3 times negative 2 is negative 6. Negative 6 times 2 is 12. So we get 14. 14 times negative 2 is negative 28. Negative 28 plus negative 4 is negative 32. Times negative 2 is 64. Plus 1 is 65. So f of negative 2 is 65. Use the remainder theorem to determine if 5 or 2i are zeros of the polynomial. So I can do that. So negative 5. Again, 3, it's another polynomial that's new. Okay, so let's do that. So negative 5, so I have 1, 6, 9, 24, 20. 1, 6, 9, 24, 20. Okay. And so I can bring the 1 down. So I'm negative 5. That gives me 1. 1 times negative 5 is negative 5. That gives me 4. 4 times negative 5 is negative 20. So then I get 4. Negative 5 times 4 is negative 20. And so I get 0. So that means 5 is a 0. Okay. And then I can do the same thing with 2i. It gets a little hairy with the complex numbers, but we can do it. So I get 1. I get 2i. So I'm going to have 6 plus 2i. 6 plus 2i times 2i. Oh gosh. Okay, so I get 12i minus 2i times 2i is 4, negative 4, 4 times negative 1, so negative 4. So I get 12i minus 4. So I'm going to get 12i plus 5. So I multiply 12i plus 5 times 2i. So let me do some space here. So 2i times 12i plus 5. So that's going to give me 10i minus 24. Okay, and so I can put that there, 10i minus 24, and so that gives me 10i. So 10i times 2i is negative 20. So that gives me 0. So that means that yes, 2i is a 0. So 5 is a 0 and 2i is also a 0. Or negative 5 is a 0 and 2i is also a 0. Oh gosh. So for the next one, I want to use the factor theorem to determine if those guys are factors of the polynomial. So the factor theorem says that if x plus 3 is a factor, then that means that f of negative 3 should be equal to 0. So I can test it. I can plug negative 3 into my function and see what I get. So I'm going to do that in my calculator. So when I plug negative 3, I'll do negative 3 cubed plus 4 times negative 3 squared and so on. When I did all of that, I got 18. So we can say that x plus 3 is not a factor. Okay, and then if this is a factor, the factor theorem says that that f of 3i should be equal to 0. So we can check. So f of 3i would be 3i cubed plus 4 times 3i squared plus 9 times 3i plus 36. So let's check it out. So when I cube 3i, let's see, 3 cubed is 27. So I'll have 27, and I cubed is negative I. And then I'll have 4 times 3 squared. So 3 squared is 9. Times 4 is 36. And then I squared is just negative 1. So minus 36. And then plus 9 times 3i is 27i plus 36. And I can see that that all adds to give me 0. And so that means that x minus 3i is a factor. So the factor theorem just relates to us the zeros and then the corresponding factors of the polynomial. Next it says find all the zeros of the function given that 2 is a 0. Write the function as linear factors, show all work. Okay, so I have this cubic and I know that 2 is a 0. So what I can do is I can start by using synthetic division to knock that down to a quadratic. So if I know that 2 is a 0, I can use synthetic division. So drop the 4 down, that gives me 8. 8 minus 20 is negative 12. Negative 12 times 2 is negative 24. Negative 24, so 33 minus 24 is 9. 9 times 2 is 18. Oh, that 18 is negative. Okay. Get 0. So that tells me that I have x minus 2, and then I have this factor 4x squared minus 12x plus 9. I can pull actually I can't pull anything out of that. So x minus 2, and so then I want to factor this guy into linear factors. I'm going to just try 2x and then 3 here and see if that gets me what I want. So that would give me, if I multiply those, I get 4x squared. That'll give me the positive 9. And then I'll get a negative 6x and a negative 6x in the middle, so that gives me what I want. So, so it factors in that way. Okay, so there is my function as linear factors. Then write a polynomial p of degree 3 in standard form with those zeros. Show all work. So, all right, so I'm going to start with it in factored form and then multiply it all out. So we'll have the zeros. So the factors that we'll have will be x plus 5, x plus square root of 2, and x minus square root of 2. So this x plus 5 is just there. This is a difference of perfect squares, so this becomes x squared plus 2. And then I can multiply this out. So if I multiply the x by both, I'll get x cubed plus 2x, and then I can multiply the 5 through, plus 5x squared plus 10. And so if I wrote this in descending order, I'll have x cubed plus 5x squared plus 2x plus 10. Oh, hang on, I had a sign error here. When I multiply these two out, I end up getting x minus 2, not x plus 2. So that should be a minus. And so that makes, actually, this guy a negative sign and that guy a negative sign. So let's clean that up. Sorry about that. Okay. Actually, hang on. So this is plus and this is minus. Sorry, these sign errors are ridiculous. Okay, minus, plus. Okay. So there we go. So there is our answer. So sorry about that sign error. All right, next one. Find all the zeros of that polynomial given that 3 and 4i are zeros. Okay. So if I know that 4i is a 0, I know that the factors associated with that are going to be x plus 4i and x minus 4i. So this becomes a quadratic, and so this multiplies out to x squared plus 16 when I multiply that out. So I can divide that out by long division, or let's do synthetic division first and then I'll do the long division. So let's do synthetic division. We'll divide out the 3. So we have choices here for what we want to do. 1, 3, 14, 42, negative 32, negative 96. Okay. So let's divide that out. Fourteen times 3 is 42. 32 times 3 is the 96. So this gives me x to the 4th plus 14x squared minus 32. And so I can just factor this guy. So I have x squared. I know x squared plus 16 is going to be 1, and so I think it works to do x squared plus 16, x squared, should be minus 2. That'll work. Okay, so these are my factors then. So I get x plus 3, x squared minus plus 16, and x squared minus 2. And so I get, if I factor this all the way, x minus 4i, x plus 4i, x minus root 2, x plus root 2. So the zeros are negative 3, 4i, plus 4, minus 4i, root 2, and minus root 2. Okay, next one. Find all the zeros and their multiplicities for this function. Show all work. Okay, so let's do the next. Okay, so I'm erasing. Okay. So, let's see, I'm on this one, 19. Okay. So find all the zeros and their multiplicities, show all work. So on 19, we don't really know what can start us out. So let's just start by graphing that guy. So 2x to the 5th plus x to the 4th plus 9x squared minus 32x plus 20. So I'm going to graph it and just see what I see as far as zeros. It looks like maybe 1 is a 0, so I'm going to hit trace and type in 1, and it looks like x equals 1 is a 0. And it looks like since it bounces there, it might have multiplicity too. I'm also looking like negative 2.5 might be a 0. Yeah, negative 2.5. So negative 2.5 is also a 0. So let's go ahead and divide out x equal 1. Maybe we'll do it twice and see where we get. So 2, 1, 0, because there's no x cubed term. 9 minus 32, 20. Okay, so the 2 comes down, 2 times 2 is, or 1 times 2 is 2, 3, 3, 3, 3, 3, 9 plus 3 is 12, 12, negative 20. Okay, and then I can pull the 1 out again, try to see if I can divide that out again. Eight times 1 is 8. 8 plus 12 is 20. Okay, and so now I'm left with a cubic. So I pulled out x minus 1 squared, and now I have 2x cubed plus 5x squared plus 8x plus 20. So I'm going to have a factor here, 2x plus 5, and then I'll have some quadratic. So to figure out what that quadratic is, I'm going to do polynomial long division and divide out the 2x plus 5. All right, so I have 2x cubed plus 5x squared plus 8x plus 20. Okay. So I'm going to multiply by 2x, and I get, or 2x squared, I get, just x squared. I get 2x cubed plus 5x squared. So when I subtract that, that gives me nothing, 0. And then I'm going to multiply by 4 to bring this down, 8x plus 20. And so I'm going to multiply that by 4. I get 8x plus 20. I subtract that off, I get 0. So then x squared plus 4 is the other factor. So and so the zeros that come up out of that are plus or minus 2i. So it asks us to, so the zeros are x equal 1, multiplicity 2, x equal negative 2.5 with multiplicity 1, and then we have x equal 2i, multiplicity 1, and x equal 2i, multiplicity 1. Oh, that one's negative and that one's positive. Okay, so those are my zeros and their multiplicities. All right, number 20, write a polynomial in degree 3 in standard form with integer coefficients and zeros, 3i and 4/5. Show all work. Okay, so for this one, we can write it all out and then we're going to multiply it out. Okay, so it's going to look like this. We'll have x squared plus 9 will be the thing that goes with the 3i and the negative 3i. And then for the 4/5, we can have 5x minus 4. Because when I set 5x minus 4 equal to 0, that gives me 4/5 as a 0. Okay, so that will work. It says it needs it in standard form. So I'll multiply it out. 5x cubed minus 4x squared plus 45x minus 36. So there it is. There's my polynomial of degree 3 in standard form. Number 21, write the domain of that function in interval notation. So the thing I need to do is figure out what's going on in that denominator, because I know that if I have values where the denominator is equal to 0, the function will be undefined there. So let's factor that denominator. So maybe 2 and 8. Okay, so we have x plus 2 and x plus 8. And so even though we have that x plus 2 on the top and bottom, still the domain is restricted that x cannot equal negative 2. So we have x cannot equal negative 2 and x cannot equal negative 8. So if I draw that out on a number line, I'm going to say everything except those places it can equal. So I'm going to get negative infinity to negative 8, union, negative 8, sorry, that's 8 to negative 2, union, negative 2 to infinity. So that's my domain. Next, find the vertical asymptotes of the following functions. Oh, so I'll go back to say that the domain is still restricted at x equal negative 2. But because I have the same factor on top and bottom, that means that there will be a hole in the graph. And since I have a factor down here that doesn't cancel out, that means that there is a vertical asymptote at x equal negative 8. So let's find the vertical asymptotes for the function next following function. So it's really going to come down to just factoring the denominator and looking at what's happening there. So if I factor the denominator here, I'll get x minus 6, x plus 3. Whoops, that's a 3. And so my vertical asymptotes are at x equals 6 and x equal negative 3. This one factors to x minus 5, and then x squared plus 16, that has complex zeros. So in fact, this one has no vertical asymptotes. There are no real numbers that I can plug in that make the bottom equal to 0. Another way to think about that is the x squared plus 16 is like the graph of x squared shifted up 16 units, so it doesn't ever cross the x-axis. There are no zeros, no real zeros of that function. The last one, I can look at this and factor the denominator. I have x plus 2 over, then I'll have x plus 2, x minus 3, I think makes that work. Yeah. And so this one is going to give me a hole in the graph, but this one here that's left on the bottom means I'll have a vertical asymptote at x equals 3, and I'll have a hole at x equals to negative 2, since I have the same factor in the numerator and denominator. Next it says find the horizontal asymptotes of the following functions. So what I'm looking at is I'm going to look at the highest power, the leading term on the top and bottom. And what I see for f of x is that the top has a higher degree than the bottom. So what that means is the top will grow at a faster rate than the bottom. So that means that this has no horizontal asymptotes. So if the power on top is greater, then it's just going off to infinity as x gets bigger and bigger. This one, the leading term on the top, on the bottom is x squared, and on the top is a constant. So what that means is that as x gets bigger and bigger, the bottom of this fraction is going to get bigger and bigger. So this whole thing is going to go towards 0. So the horizontal asymptote here is going to be y equals 0. That whole thing is going to go towards 0 as x gets bigger and bigger. Now the next one, I note that the powers on the top and bottom, the degree of the top and bottom, are equal to one another. So that means the top and bottom are growing at roughly the same rate. Although the top is growing 2 times x squared, and the bottom has 3 times x squared. So my horizontal asymptote is going to be y equals 2/3. So the top is 2 times x squared, the bottom is 3 times x squared. So that's the proportion in which those two are going to grow as x gets bigger and bigger. Okay, for the following functions, determine if a slant asymptote exists. If one does, find it, show all work. Okay, so for this one, I'm just going to notice that the degree of the top is cubic and the bottom is x squared. And so if I divide that out, I'm going to get a quadratic function. So that means that there are no slant asymptotes. And for the next one, I see the degrees are going to work out. So I have a cubic and a square. So when I divide that out, I should get something linear. Let's go ahead and do the division and see what we get. So if I do x squared plus 0x minus 5, I'll have 2x cubed plus 3x squared minus 5x plus 2. So when I do that division, I'll multiply by 2x cubed plus 0x squared minus 10x. So if I subtract that off, I get 3x squared plus 5x plus 2. So if I multiply this by 3, I'm going to get 3x squared minus 15. And so I subtract that off, and I get a remainder of 17. And so what that, 5x plus 17. And so what that tells me is that this up here, the 2x plus 3, is my slant asymptote. Why? Because what I'm saying is that this thing is equal to 2x plus 3 plus 5x plus 17 over x squared minus 5. And this guy is going to go towards 0 as x goes to infinity. Okay, so I want to graph this function by hand. Okay, so the first thing I want to do is look for, I can see right away what the horizontal asymptotes are going to be, because I see that the degree of the top and the degree of the bottom are the same. So the horizontal asymptote is just given by the coefficients of the leading terms. So it's 2 over 1. So the horizontal asymptote is I'll write it as y equals 2. So I can put that in here as my horizontal asymptote. And then for vertical asymptotes, I can go ahead and factor the top and bottom. So it looks like on the top I can pull out a 2x and I'll get x minus 1. And on the bottom, looks like I can do x, 18. So 6 times 3. So we'll do 6 and a 3. And I want the 6 to be negative. Okay. And it looks like I don't have any factors that are common to the top and bottom. And so what that means is that both those bottoms are going to produce horizontal asymptotes, or vertical asymptotes. So my vertical asymptotes are x equals 6 and x equals minus 3. So I can go ahead and put those in. Okay. And then so my domain will be everything except negative 3 and 6. So it'll be negative infinity to negative 3, union negative 3 to 6, union 6 to infinity. For the y-intercept, I can plug in 0. If I plug in 0, I can see that the top gives me 0. So it goes through the point 0, 0. So I can label that point on my graph. And the x-intercept, so if I set that equal to 0, 0 equals 2x times x minus 1, I can see that I have a 0 when x equals 0, and I have a 0 when x equals 1. So when x equals 1 will also be a place where it goes through the x-axis. So that's right here. It seems a little weird that they're right next to each other like that, but anyhow, we're going to end up with something kind of like this. It's kind of dancing around these asymptotes there. And then, so the x-intercepts, we have 0, 0, and then we also have 1, 0. For vertical asymptotes, again, I said x equals 6 and x equals minus 3, and horizontal asymptote y equals 2. If a graph crosses a horizontal asymptote, where? So how do I find out that? So I think I set that equal to 2. So if I say 2 equals this guy, So if I set that equal to 2 and then solve for x, I guess. So let's pretend we did that. Then, oh gosh, okay, well maybe it's not that hard. Okay, so I'm going to multiply that over, so I'll get 2x squared minus 6x minus 18 times 2 is 36. Okay, and then I can move everything to one side, and so I'm going to subtract 2x squared from both sides, subtract that 2x, I get negative 4x minus 36 equals 0. I can add that over, I'm going to get x equals negative 9. So it does cross at negative 9. So negative 9, 2. And then my slant asymptote, I have none. Okay, and so, and then we'll throw in some additional points. So I kind of see what's happening in the middle of the graph. I don't know what's happening on the either side, so we can try like maybe what happens at 8. Maybe we can see what happens at like negative 4 and see where we are. So if I plug those in, I'm going to see that it's up above the graph here, and it goes like this. Okay, and so yeah, just plug those numbers into the original function and you can get some outputs there and then plot those points and do it. So that is that.